All right, happy Tuesday, everybody. It's good to be back here. We had actually, what am I thinking? We were back last week, weren't we? Exploring that new CCNA last week. It just wasn't a technical session. So in my head, I'm like, oh boy, we didn't do anything last week. It was actually a lot of fun and very important. So if you happen to miss that, if you're studying for your CCNA, be sure to go back and watch that video in the archives because the CCNA is crazy, the new one, and all this programmability stuff. So be sure to touch on a lot of that again in that session last week. So today we are switching gears a little bit, going from the non-technical world back into the technical, and we are looking at CCNP level content. So I have the privilege at CBT Nuggets of making ENCOR content, and ENCOR, ENCOR, kind of a weird way of saying it, but ENCOR stands for Enterprise Networking Core. So it's Cisco's Core Enterprise Networking exam, and that's the key exam for the CCNP this time around. So Cisco has renamed their RNS track the EN track. So RNS, Routing and Switching, has become Enterprise Networking, or EN. And again, now the CCNP Enterprise Networking, the CCNP EN, is focused on this, or centered around this ENCOR exam. So again, it's a lot of fun making this content. I actually just went through FHRPs in the ENCOR playlist, and so we're going to be diving into those a little bit tonight. We'll see how long it takes to get through all of the whiteboarding, chalkboarding of the FHRPs themselves. And ideally, we have some time at the end to actually log into the lab and take a little look at some of the lab configuration. Hey, Ben Zahar, how's it going? Thanks for saying hi. All right. So as far as the agenda is concerned, so we're looking at FHRPs tonight. Again, anytime we're talking about first hop redundancy protocols, it's going to come down to three main topics. We're going to be looking at HSRP, VRRP, and GLBP. Those are the three main protocols that fall into that FHRP category. But we want to start off just by making sure we're all on the same page, defining why FHRPs are important, what they're accomplishing, what they can do for us, and then, oops, hey, Big Papa, you stick around as long as you can, full evening tonight. All right, very good. But hey, thank you very much for extending your subscription. Very good. And we are actually moving up in the world. We're no longer, we're looking at some ENCOR content tonight, so stick around as long as you can, for sure. This is a little bit of a sneak preview of what CBT Nuggets is working on behind the scenes here. So, again, we're going to be looking at FHRPs, VRRP, HSRP, GLBP, all three of the something P's, right? A lot of these protocols. And then ideally, again, we'll get into the lab and do some configuration. So let's go ahead and jump in here to the whiteboard and try to figure out what all these FHRPs are about. So I'm guessing most of us on some level understand the goal of FHRPs. But just to kind of recap here, get us all on the same page, the idea tends to be that, let's say we've got some users that are logged into a network, and let's just use the example that, where there's an upstream router. So like maybe a long time ago, back in the day, however you want to say it, we had a single router, and this was the default gateway right here. So maybe this is the 192.168.1.0/24 network, and we've got .1 here as the default gateway. So what that means is these PCs, that we configure them for a default gateway of .1, each one of them individually, and that means that anytime they need to talk to something outside of the network, they're going to go out through their gateways, which, again, we're comfortable with at this post-CCNA level. So the idea here is this. Once upon a time, we looked at this and said, okay, this is great, but we could use some redundancy. And so the redundancy is going to look like this. We're going to throw another router onto this network. And these routers, this could be any layer 3 device. So this could be a layer 3 switch. It could be a router. Maybe that's the extent. It could be a firewall, technically, actually. So really, any layer 3 device could be our default gateway. And so we're going to assign this to .2. And wouldn't you know it, use the big bad red color here, wouldn't you know it, one of these routers goes down. It happens to be the one that we've configured for .1. And we say, okay, no problem. Router number 2 is back, or is still there. We paid extra money to buy another router and have it ready for redundancy. And once you know it, the network still goes down. And the reason the network goes down is because we're still pointing our default gateways to .1. And .1 is gone. We lost .1. So what are we going to do here? Well, one of two things. Either we come to this router and we replace it, or reconfigure it, really, and say that this is .1 now, you are .1 now, and hey, all of my machines are back online. But that's going to cause problems if router, that first router comes back up. And, it's probably not best practice to do that. I mean, I guess we could go around to every PC in the network and configure it for .2, but that's not prudent either. So clearly we need a better solution, and that third option for us is going to be, hey, guess what? First hop redundancy protocols. So the idea here is going to be this, and because I didn't make myself a new layer, I'm going to have to redraw that, but that's fine. No problem. So we've got two routers. We know the situation now. These two routers are on one network segment. So again, we've got multiple PCs down here. And let's just say the gateway for all of these PCs is once again .1. I need to make sure I don't draw on my face again, or under my face. Hey, Papa, send help desk staff to change the user PCs. Yeah, that's that sneaker net concept, right? Put on your sneakers and start running around to get it going. I don't know. I've never heard of a story like that, but I have to think that those stories exist from, mid 90s or so. I don't know when HSRP really came out, but I mean, there had to have been networks where like, okay, the gateway's down, we've got to go out a different way. Let's reconfigure IP addresses to make that happen. By the way, tonight's stream is sponsored by Mr. Keith Barker, the OG of IT. He sent me this great shirt in the mail, so I really owe him one for that. He even signed it over here and said, "Jeff, you rock, Keith Barker." So I really appreciate Keith sending me this shirt. I was like, I am wearing this on my stream tonight. Got to do it. All right, so where was I going with that? Okay. So the idea here is this. Let's not assign the gateway address .1 to either one of those routers. Let's assign, let's say, .2 to the router on the left and .3 to the router on the right. Let's just give these names because we're going to keep referring to these guys as something. So router 1 and router 2. Then what we're going to do is we're going to share an IP address. We'll call this .1 here now as a virtual IP address, or that VIP concept. And a virtual IP address simply means that nobody owns it on a physical piece of equipment. It just sort of lives in the ether, in the virtual layer, or what have you. And so one of these routers has to own it at a time. We can't have both routers claiming to be .1. That would be a true duplicate IP address. And we don't want duplicate IP addresses on the network. That would be bad. So only one can have .1 at a time. And so let's say we've got this primary and secondary concept. So primary and a secondary. So now the primary owns .1 for right now. And then, hey, I'm going to remember to do another layer this time. There we go. So then, wouldn't you know it again, of course, router 1, the primary goes down, takes down that .1 IP address. Well, fortunately, we are running this FHRP, first hop redundancy protocol, that manages this virtual IP address. Therefore, the virtual IP address now shows up, magically, on the secondary router. And because of this, the PCs that were going this way 1 moment ago will now switch over and go this way in a brief moment. Pretty quick. This can happen if we tune our timers right and everything. I mean, all this can happen in less than a second. Okay, so this happens very, very quickly. It definitely matches the needs of modern networks, because even when HSRP came out, the default setting is like 10 seconds for it to default, or for it to detect one of these. The primary has gone down, so the secondary is going to sit there for 10 seconds and wait, and then it'll flip over, and then it usually takes another second or two to converge. So you're talking about 10 to 15 seconds potentially of outage because one of your redundant devices went down. Instead, we tune those timers now in this day and age to be sub-second timers. So maybe now instead of every 3 seconds we're sending hellos, we're sending them 3 times a second, or every 300 milliseconds. And then instead of waiting 10 seconds, we wait 1 full second. Because we can't wait 15 seconds. And truthfully, on these network switches that we have today, I mean, I'm trying to even think of why we'd wait that long. I think just like processing power on the routers and sending them and network bandwidth, I guess. But, even back in the 10 meg days, there shouldn't have been much bandwidth. So, all right. So now we have our solution. This is FHRPs, but there's going to be a lot that goes into making this work. Okay. And this is where, everything we've covered up until now is probably that CCENT, CCNA level of understanding of first hop redundancy protocols. But when we want to understand this at a deeper level, going into that ENCOR CCNP level, we need to understand what's going on the network to make this happen. And so one of those concepts is we're going to have to talk about ARP and layer 2 virtual MAC addresses. So let's go ahead and talk about that. I'll get rid of my bad layer there. We'll go back to the other layer. And we'll choose a different color here to keep things fresh. Okay, so what's going on underneath the behind the scenes? So there's a concept of a virtual MAC address at play here. We've mentioned the virtual IP. That's a little easy to understand. Okay, it's an IP address that's being shared. But what happens? How do we get from these PCs out to wherever we're trying to go? When we're sending traffic to the default gateway, what is our destination IP address? Our destination IP address is not .1, because if our destination IP was .1 and .1 received it, it'd be like, what do I do with it? Our destination IP is out here in the rest of the world, wherever we're trying to get. It could be the next network over on the other side of that router. It could be across the internet. But either way, the destination IP address never changes, short of network address translation, but we won't go into that. For now, the destination IP address never changes, and therefore, we need a way for this router right here, router 1, whatever our default gateway is, we need that router to be able to pick up that packet and know it's destined on the local network for it. And of course, local network addressing should trigger us to think about MAC addresses. So if we have a virtual IP address that is shared between two routers, well, guess what? We're going to have a virtual MAC address as well that's shared between those two routers. This virtual MAC address is going to be bound to this .1 address. So just to kind of clear, oh, you know what? I went back to the other. That's fine. We'll get rid of all this just because it's a little noisy. We'll leave VMAC there. So now we not only have a virtual IP address, we have a virtual MAC address. I didn't learn my lesson. I didn't add a new layer. There we go. So this virtual MAC address is at the heart of what makes all of this work, because what is going to happen here is that this gateway, let's say this host right here, does an ARP for .1. Steady state operation, both routers are up. I need to send traffic to and through my default gateway. What do I do? Well, if I've never sent anything to my default gateway, I don't know what its MAC address is. And this is the concept of ARP. I know I've been pre-configured, hard-coded with my default gateway being .1. Now, that might be... saying it's hard-coded is a stretch because it's still DHCP, right? I've dynamically received my gateway address. It's .1. But that's all I know. I didn't get the MAC address from my DHCP server. I only know the IP address. So I ARP for it, and I say, hey, who owns .1 as the IP address? And the primary is always responsible for responding to those ARP responses. Technically, either one could respond to it, but we don't want the chaos of it being a free-for-all, or maybe both of them respond, and that could be confusing. So the primary is going to respond by sending an ARP response, and that ARP response will give it this virtual MAC. So maybe this virtual MAC address is A. I don't know. We just keeping track of the different virtual MAC addresses here that we're talking about. So I guess, no, either way, doesn't matter. So now we've got .1 as a gateway address. We know that that's my IP address. I've done an ARP, and I've gotten back the virtual MAC address. So now I understand that not only do I have my default gateway IP address, but I also have my default gateway's MAC address, which would be A in this case. Now I can send that packet to my default gateway, and the way I do that is I keep my destination IP address focused on the end destination, google.com or whatever I'm sending my packet to, from an IP address perspective, of course, so google.com is a bad example. But I've got my destination IP address, and then my destination MAC address is always going to be for my default gateway. So my destination IP will be whatever my destination MAC address will be the gateway's MAC, that virtual MAC address. So because I have now sent this packet up, everything is good. It forwards it upstream. It gets it out to the internet or what have you. Life is good. And again, we have this scenario where this router has now gone down. So we know that we take on the virtual IP address. We probably need that virtual MAC address, don't we? And the answer is yes, we do. And so we're also going to take on that virtual MAC address. But there's a problem with this, and it requires a different type of drawing. Look at it from this perspective. Here's a switch. It could be a series of switches. It doesn't really change in a layer 2 environment. And I've got my 2 routers living out 2 of these interfaces. And I've got my PC, I'll just do one PC living out this interface. Now this is a layer 2 switch at this point. It could be a multi-layer switch, it doesn't matter, but we're talking about the layer 2 operation of this switch. And we have on every layer 2 switch this concept of a CAM table. CAM stands for Content Addressable Memory. And the fun thing about that is it's actually there's a lot of meaning in those words. It's kind of weird to say, well, wait a second, it's the MAC address table because we store MACs here. So MAC, Media Access Control, that's what MAC stands for. At least as long as you're not talking about Macintosh computers. But a MAC address, Media Access Control, MAC, CAM, C-A-M is backwards. Why do we call them a CAM table? Why don't we call them MAC tables? And we certainly do call them MAC tables. There's nothing wrong with that. If you said the MAC address table, everybody's going to know what you mean. In fact, a lot of Cisco commands are centered around show MAC address table or what have you. So yeah, we all know that there are MAC address tables. So why content addressable lookup? Well, a content addressable lookup, this is a little bit of an aside, but it's actually kind of interesting. Because if we do a memory lookup, and random access memory, we're talking about normal PCs, usually what's happening is an application is going to store data in a memory address. And so later, when that application needs that data, it provides the address to get that data back. And then the memory sends the data that's at that address. That's a standard memory lookup. A content addressable lookup is backwards. It's this concept of being, again, we're flipping it on its head, because what we're doing is we're actually, for a CAM, we're providing we are on this phase. We're kind of skipping this phase because Switch does the phase where it populates the table, okay? And so for this phase right here, rather than the app providing the address, the app actually provides what we call the content. In our case, the content is a MAC address. And the response is technically, we could call it the memory address. I mean, technically that is what's happening. And then we use the address to figure out what interface to send something out. So I just thought that was interesting and worth sharing, kind of a little bit behind. Again, this is supposed to be a little bit more of an advance of a conversation. So this content addressable lookup concept goes beyond Cisco, goes beyond switches, goes beyond networking. It's a memory computer level function. But I will say that most, you search for addressable memory lookups, you're going to find a lot of examples pointing to networking, because networking relies on content addressable lookups very heavily at this layer 2 operation. So that's neither here nor there. That was just sort of a fun aside. So we have this CAM table, content addressable memory lookup, or content addressable memory table. And this CAM table gets populated. Remember, we said we skipped this phase up here because the switch is doing that. But really what's happening is that as packets get sent, we know that this CAM table is getting populated. So the CAM table says, let's just give these numbers here. Let's say that this is MAC address A, this is MAC address B, this is MAC address C. And you know what? Let's just go ahead and give us a 4th host, because we'll need that in a second. Meanwhile, let's also call these ports 1, 2, 3, and 4. So this CAM table is going to look something like this. Port 1 has, well, actually, let me draw it out. So port MAC. And by the way, a third data point, a third data entry is, I know I'm kind of right over my head here, is the VLAN. So you can look at one of two ways. You can say that the MAC table is partitioned out by VLAN. Technically, it's not. Technically, the VLAN is just a parameter in the table. But I like to think of it as if every VLAN has its own CAM table. It's just sort of the right way of thinking about it, in my opinion. But we're not talking about multiple VLANs right now, so we're just gonna leave that out. All right, so we've got a mapping. So this router starts speaking on port 1. We learn that MAC A lives out port 1. Same thing with port 2. Router B starts speaking, and MAC address B shows up on port 2. Well, think about this. As soon as C speaks, let's say C sends that ARP request, and that ARP request is asking for the virtual MAC address. So what did we say happens? The primary is going to respond. So let's say the primary here is on the left, secondary or standby is on the right. And because we've sent this ARP request out port 3, first of all, my MAC address is C on port 3, and so the switch is going to learn out port 3 is MAC C. I'm really trying hard to stay within the parameters here. Make sure you guys can still see it. And then this ARP response comes back. And the ARP response, change colors here. This ARP response comes back in. It's an ARP response. And its MAC address is, let's just call it V for virtual MAC address. So now we've just learned that out port 3 is also this virtual MAC address. Okay, I guess that's the last entry I can make in the port MAC table. All right, so the switch now knows that virtual IP address lives out port 1. I said that wrong. Whoops, there we go. 1. The virtual MAC address lives out port 1. And so next time now, let's say my PC now wants to send a packet to that virtual MAC address, again with the example we gave, well, now the switch knows to forward that packet out port 1. All right, so that's good. That's great. Everything is good. I really do need a little bit. I'm going to have to move my face here. Classic situation. Let me see here. There. All right. I'll move me back here in a moment. All right, so, and there. Now, let's talk about that failure scenario. As soon as my machine responds. There we go. Now let's talk about that failure scenario. So this router now goes down. And we just said that this router right here, router 2 or whatever we want to call it, now we're representing the virtual IP address. Now we're representing the virtual MAC address. Do you see the problem? I'm gonna take a drink break here just for a second. I'm gonna sip my water and you try to figure out what's the problem here. Because there is a problem, and it's right there on the screen. Here's the problem. Host C wants to send another packet to its default gateway. So it sends that packet. The switch, upon receiving and we call them packets, but they're layer 2, they're frames, right? So the switch receives that frame, and it looks at its CAM table. Where does MAC address V live according to its MAC address table? It lives out port 1. Now, port 1 might have gone down, like the router actually died and there's no electrical connection out of it, and so therefore this entry was cleared. And I guess the good news is if there's no entry, if that entry was cleared and there's no entry, then it'll get flooded out all of the interfaces. And that's a decent situation, actually. It's why switches behave this way, is to catch these situations where it'll flood unknown traffic everywhere. However, we do have a better mechanism, because there could be a problem where that router, maybe it lives out another switch, or maybe it's not directly connected to the switch, or some situation where the port is up, but the router is actually still down. All right, so what could have happened, or what can we do to awaken the switch to the fact that the virtual MAC address now lives out port 2, because that's where it lives now, right? Well, there's this concept of a gratuitous ARP. And maybe you've heard of this and maybe you haven't, but a gratuitous ARP, we call these GARPs, because we love our acronyms in networking world, that's for sure. A GARP, a gratuitous ARP, is essentially an ARP request that nobody asked for. I said request. I meant response. There we go. An ARP response that nobody asked for. Nobody sent a request, therefore there's no reason to send a response, right? Well, in this case, there is. So nobody said, hey, .1, where are you this time? What the reality is that this router 2, and really baked into the protocol, we know that we have this problem with the CAM table. So if we send a gratuitous ARP, what happens as soon as that frame hits that switch port? Switch is going to do what a switch is going to do. It's going to say, okay, out port 2, this virtual MAC address now lives. Now, anytime a switch gets a new entry for an old MAC address or an existing MAC address, it's going to clear out the old entry. So it will clear this out. It will assume that the virtual MAC address moved. In this case, indeed, it did. The network according to GARP. Yeah, exactly. GARPs. I tell you what, GARPs are very. They're used a lot in the data center space. UCS uses GARPs all the time as things move around. VMware, anytime there's a vMotion, GARPs all over. So it's a funny word. It sounds weird to say, but we absolutely use GARPs a lot for this particular application. So this is what's happening underneath the hood of a first hop redundancy protocol in order to converge the network. Because yes, we need to converge layer 3, and we kind of do that. I mean, the last whiteboard drawing was focused on converging layer 3. It was simply IP address is now managed by this router. But we have to converge layer 2 as well. We want to converge that quickly. And so a GARP is the fastest way to converge the network, layer 2 network, as to where it lives. Again, keeping in mind that this might not all be directly attached. So this GARP is going to, it's an ARP response. It gets, it's going to get flooded. It's going to get flooded throughout the entire network. And so, every switch in the network is going to learn where this virtual MAC address lives. All right. So, moving on, I think we're ready to talk about specifics now. Maybe a little bit. That would be nice, right? So let's go into the wonderful world of HSRP. I need to move my face back, I think. There we go. All right. Let's get off of that ugly red color. We don't have any outages yet. You can bet we're going to get some outages here soon. Okay. So, HSRP. Now, these FHRP, this FHRP concept was developed and invented by Cisco. All right, leave it to Cisco. This happens all the time. It's a tale as old as time. Wow, I can spell Cisco with 2 I's. That's exciting. Tale as old as time. Cisco is on the scene because they have enough of a base, enough of a, I guess, I don't know. Again, I was going to try to think of another word besides base. But they have a lot of Cisco routers and switches out there. And so when there's a problem that arises in the industry, what happens a lot is Cisco will create a solution for it, push it out in software to all of their switches and throughout the world or what have you. And so now Cisco users can get around that problem. Meanwhile, non-Cisco switches can't. And so the industry, the IEEE or the IETF, will usually work with Cisco to create a new industry standard around that topic. So in our case, Cisco invented the Hot Standby Router Protocol, HSRP. And the Hot Standby Router Protocol worked great, only on Cisco devices because it was a Cisco-only solution. And then the industry wrapped its arms around the idea of the Virtual Router Redundancy Protocol. That would be the industry standard version. And then Cisco had another idea, and so they decided to create another FHRP called the Global Load Balancing Protocol. And incidentally, they updated HSRP via HSRP version 2. Okay? So these are, call it 3 main routing protocols, first hop redundancy protocols. We have HSRP, VRRP, and GLBP. And we do need to know a few of the differences in HSRP version 1 versus HSRP version 2. So I'm not sure. We'll try to cover some of that tonight, but we'll see where we land with that. It's there's a lot to cover in this topic, and it's already been 30 minutes, which is crazy. Time flies. Okay, so HSRP. The best way to learn FHRPs, in my opinion, is to kind of pick one, and I'll just pick HSRP because a lot of networks still use HSRP, and especially since, we're talking about ENCOR, which is a Cisco level exam. So, hey, we'll stick with the Cisco protocol. But once we learn HSRP, VRRP is really easy to learn. It's just really the same thing, just with some differences, and so we'll learn those differences. And GLBP, kind of the same thing. It's a little bit different than HSRP in a very specific way. So we'll start off with HSRP and figure out how this works. Now we know the gist of how these FHRPs work, so we don't need to go into all of those details, but we are going to need to talk about a few of them. Get a new layer here. There we go. Okay. So first and foremost, HSRP, all FHRPs are configured in groups. What a group means is I might have, for example, 4 or 5 routers on here on this network segment, and 2 of these I'm going to pair together, and these 2 I'm going to pair together. And if they're all talking HSRP together, I can't have them all intermingling, right? Because I just want the 2 green ones to be together. I want the 2 blue ones on the right to be together. I don't want them interfering with each other. And this is where groups come into play. So groups, I could assign a group to this set of routers and say, okay, you're group number 1. And I could assign a different group to these 2 routers and say, you're group number 2. The most common situation where you see that groups are overlapping tends to be a situation like this, where you have 2 routers on one side and they're talking to 2 other routers on the other side. And a lot of times this is a service provider pair of routers, and this is sort of a DMZ network out on the internet edge, and these are my internet routers here. And so I'm running HSRP this way, they're running HSRP that way, and now all of a sudden we could all 4 of these routers think that they're all on the same HSRP or in the same HSRP domain. And we don't want that. They're sharing different virtual IP addresses, virtual MAC addresses, different networks behind them. And so we don't want them all to share. We want 2 separate pairs. And this is, again, where the benefit of having groups comes into play. So in HSRP version 1, I'm just going to clear that out because that got busy. In HSRP version 1, we get 256 groups. Sounds like a lot, right? Sounds plenty? All right. And yet, HSRP version 2 gives us 4,096. Now, holy smokes, Jeff, why? 256 was plenty. Why are we going to 496 or 4,096? There actually is a good reason for this, okay? Number 1, if I have a multi-layer switch, I'm trying to think of how to draw this multi-layer switch. I'm not great with my network symbols sometimes. If I have a multi-layer switch and I'm running HSRP on a SVI, switch virtual interface, this is a VLAN interface. And what do VLAN interfaces have? They have a VLAN ID. So maybe this is the VLAN 10 interface. So if I have the VLAN 10 interface and I'm going to configure an HSRP group, what group ID do you think I'd like to use? There's no technical reason for picking any particular number. I could use HSRP group 17. I could use HSRP group 178. I mean, I can use whatever HSRP group I want, but from a human perspective, from a readability and organizational perspective, I'm going to configure HSRP group 10 because that looks pretty. And in troubleshooting, I mean, when you're troubleshooting a network and like the network's down and people are, screaming about getting it back up online and you're frantically punching away at the keyboard, or other people who aren't familiar with this network are maybe consultants or Cisco Tech. I mean, they're hammering their keyboard and they're trying to fix a problem. This kind of organization helps because we all kind of get this concept. So we want to align the HSRP group number with the VLAN ID. That sounds great. That might be why we have 256 groups in HSRP v1, because now, I don't need more than probably, maybe 8, maybe 16. In fact, early implementations of HSRP, some routers you'll find only support 16 groups. So, and that's just a software limitation that, and potentially hardware, has nothing to do with the protocol. The protocol can support 256. And that sounds like plenty, but again, now I'm going to configure HSRP on my SVI, and this VLAN interface is 499. Okay, that's fine. VLANs can go all the way up to 4096, so I'm going to configure what? HSRP group. Ooh, I only have 256. I can only go 0 to 255. So I can't actually match VLAN 499. Like maybe 99 is available and I could try to match that. Or maybe I could call it 49 to match the first 2 digits, but I can't directly match 499. This is why with HSRP version 2, Cisco gave us 4096. So we can match whatever VLAN ID, because guess how many VLAN IDs are there? 4096. So if we have VLAN 499, I can have HSRP group 499. If I have VLAN 3692, I can have HSRP VLAN or HSRP group 3692. I don't even remember what I said, but you get the point. All right. So the number of groups is different between HSRP version 1 and HSRP version 2. And for the ENCOR exam, I would remember that. There's a lot of facts around first hop redundancy protocols. And so I would not hesitate to spend a half an hour to an hour just memorizing this, among other things we're going to mention here. Okay, next concept. Change colors here. Next concept is priority. Okay, so we're on the same group. Maybe we've configured group, what do we say over there? 10. So we've got group 10 configured on both interfaces. We've got this virtual IP address configured. By the way, the virtual IP address is the only thing you have to configure on an interface to activate FHRP. So, and FHRP. So like HSRP, for example, if I want to activate HSRP on an interface, all I have to do is get on there and type the words standby, because Cisco didn't use HSRP as the command. Standby, and then optionally enter the group ID, otherwise it defaults to group 0. But probably standby 10 IP and then the virtual IP address. That's it. If I do that command on both routers on those interfaces, HSRP is active, they'll communicate with each other, and you have yourself a redundant network. That's all. That's all you have to do is that one command. It's pretty awesome. But we like to tune things. We like to be in control. We don't know, like, for example, who's going to be the primary and who's going to be the secondary. Now, in HSRP, again, is one of those memorization things. We do need to memorize the names, the types of primary and secondary. Hey, Keith, thanks for stopping by. I should hope you love the shirt. I love the shirt. Thanks again for sending that. Talking about FHRPs tonight. Little preview of the ENCOR content that's coming out here, hopefully soon. So what we've got here is, I have to remember what I was talking about. We're talking about who is the primary. Okay, I remember now, because the names are important. In HSRP and Cisco land, we call this active and standby. We do not call them primary and secondary, for example. I like to use primary and secondary generically when talking about FHRPs, because guess what? As soon as we get to VRRP, it becomes master backup. So, of course, we can't ever just use Cisco's words because we don't want to get, I guess, sued by Cisco technically. I don't know how exactly that works. But the assumption here is, Cisco called it active standby. We're creating an industry standard version. We don't want to call it the same thing. So active and standby are important. Those are the Cisco verbs, terms, whatever. And we need to keep that in mind. So back to the original question. How do we determine the active versus the standby? Well, it's this concept of priority. And we talk about this. We've mentioned this a couple times in this study group, so if you haven't been part of this, I'll repeat this. When it comes to priorities and elections and things like that, sometimes in networking, the higher number wins. Sometimes in networking, the lower number wins. And it can be difficult, to say the least, to try to keep track of when it's higher and when it's lower. Here's the rule of thumb that I give to help with this situation. And keep in mind, it's a rule, which means there are exceptions to every rule, right? So there will be exceptions to this. But I tell you what, keeping this rule in mind will help lay the foundation so that you can hopefully just remember the exceptions, okay? So here's the rule. If it's a layer 3 protocol, the higher number wins. If it's a layer 2 protocol, the lower number wins. Again, I want to emphasize, is this always true? No, it's not always true. But in a lot of cases, it is. So let's walk through a couple of those. So spanning tree protocol, layer 2 protocol, right? The lower root bridge ID will win in a spanning tree election process. Multicast is interesting. Do you know there's a layer 3 element of multicast called PIM and a layer 2 element of multicast called IGMP? Well, when it comes to elections, the PIM DR, designated router, the higher number wins. But the IGMP router is going to win the election if it has the lower IP address. And that's with intention because they don't want the same router doing both functions. And it's just, they split it up that way. We have OSPF priorities, right? OSPF DR, the higher number wins that. And yeah, we're talking about FHRPs, so FHRPs fit into this as well. I will tell you the one that always comes to my mind that breaks this to some, it definitely does, is administrative distance. Because administrative distance, the lower number wins and the lower metrics. But that's because, it's because we're talking about distance and we want a lower distance. So it is sort of its own category. But at the same time, that's a layer 3 concept and it does break this rule. But a lot of our elections, we can hopefully try to remember this. So when it comes to FHRPs and you're trying to remember, is it the higher priority or the lower priority? FHRPs that's a layer 3 concept. And so the higher priority is going to win. Okay, so all that to say, the priority will determine who's the active and who's the standby. What's the tiebreaker? Because we might have the same priority. In fact, in a lot of cases, we do. The default priority is 100. And if I don't change it, we're going to have a tie in priority on both of those routers. Well, the tiebreaker will always be the IP address. So let's say that this is, what did we say earlier? .2 and .3, I believe we went with. So let's say we have .2 and .3 on these two routers. And so we're going to look at the physical IP address, not the virtual IP address because they share that. We're going to look at the physical IP address and see .2, .3. Okay, well, .3 is going to win that election. And so technically, as I have this written out, it's backwards because the standby is .3 and the active is .2. But we can take control of this. We want the network as deterministic as possible. I want to know that this router is the primary or active. This router is the standby. I want to know that. Maybe it doesn't matter from a technical perspective, but we want to know where our traffic is going. Therefore, we're going to set priority in order to force the issue. So a lot of times what we do is we set one router to be 110 and the other routers to be 90. Because that makes sure that the standby is always the standby because it's less than the default, which is 100. And the active should always be the active at 110, as long as we're talking about comparing to routers that are attached that we keep the default. So that's this concept of priority. I can set this priority, by the way, to be between 0 and 255. So we can go all the way up to the top of that number. We can go all the way to the bottom. Either way, higher priority wins. Okay. So now we have our active, now we have our standby, and we're going to have to check, I suppose, to make sure that our active is still online. Well, this would be a familiar concept. It's used in routing protocols, which is going to be used in first hop redundancy protocols. We're going to have timers going back and forth. I say going back and forth, but, really the active is sending these hellos, and the standby is receiving those and processing them and thinking, oh, okay. And I believe it does go back and forth, actually, because the active does track the standby status as well. Either way, these timers, by default, are set to 3 seconds for the hello, and the 10 seconds for the dead timer, or the, I believe it's called the hold timer in HSRP. By default. This is just by default. So I'm supposed to be getting a hello packet every 3 seconds. If I don't get any packets in 10 seconds, I'm going to assume that the other router is dead. And if I'm the standby, that means I'm going to take over for the active. So this works in the scenario we described before, right? Like, okay, this active router goes down and standby's got to take over, but it will wait 10 seconds by default. Can we wait 10 seconds? It depends on your network. Depends on whoever makes the decisions. They can decide that, right? It's not always on the network tech. However, in modern networks, we do like to change those timers. We like to tune them down. Again, we can go sub-second timers. In fact, we can even leverage something called bidirectional forwarding detection. I'm not going to go into the details on BFD, but BFD is sort of call it a generic way of tracking another router's state. And once you've established BFD relationships, you can actually apply BFD settings to any routing protocol you want, any FHRP you want, any with an asterisk, because I'm not sitting here promising that's going to work with every single thing you can configure on a router. But what's nice about bidirectional forwarding detection is you can get down really, really granularly. Like I don't exactly know how many milliseconds, but it can go very, very. It's designed to go very, very fast. And so it sort of offloads. Instead of saying I'm going to rely on HSRP timers, I can actually rely on BFD instead of the HSRP timers to track if the other side goes down. And again, we can use BFD in OSPF and EIGRP and all kinds of other things. So that's definitely an option for us. Now, worth mentioning, by the way, millisecond timers. So we're not talking BFD now. We're talking about native HSRP. We have to have HSRP version 2. If we don't have HSRP version 2, we can't do millisecond timers. All right, I had that in my notes, so I just wanted to toss that out there. Okay, last couple concepts here. So first of all, I'll just mention this. We're not going to go into detail. We can do authentication. Okay, so we can basically require a password. And yeah, we can do this in clear text, bad idea. And we can do it using an MD5 hash. That would be the good idea. So generally speaking, just configure MD5. It equates to a password. There's, you can use a keychain. And we saw that when we did HSRP or EIGRP configuration a little while ago. But you can also just configure a string onto the interface. That's usually good enough. So yeah, we always recommend that we lock that down. I will say this, HSRP authentication is usually more about just an added layer of protection against accidental fat finger configurations. So let's say you replace one of these routers at one point, you've got it on the shelf, it's a lab router, and somebody decides, I'm going to grab this router off the shelf and I'm going to attach it to the network and configure it. And they plug it in, and immediately, because it was the primary in the past, it takes over as primary and takes the whole network down, and that's not ideal. So having MD5 passwords, it's just another layer of security to make sure nobody accidentally joins this HSRP group. But certainly, it's going to protect against the malicious situation too, where somebody actually does try to take over. If you have a bad guy here that network sniffs and sees HSRP traffic, he could technically decide that I'm going to join this HSRP group. I'm going to make all of these hosts send their traffic to me, and then I send all of the traffic up to the active. It's called a man-in-the-middle attack. The user has no idea that there's a man in the middle. We're sending all of our traffic to the bad guy, and the bad guy's sending it all onward so that we are none the wiser. And so maybe he's gleaning data from us by way of this man-in-the-middle attack. That's no bueno. So definitely configure authentication on your HSRP configurations. Last step is preemption. So this concept of preemption, let me make this drawing a little bit more clear. Yeah, we'll just do that. Okay, so preemption. So let's say we have a priority of 110 here and a priority of 90 here. And so this is our active, good. And here's our standby, also good. And then, wouldn't you know it, gee darn, this keeps happening, our primary goes down. So our primary router has gone down. Our standby has now become the active. But lo and behold, with that router just hit a bug, it reloaded, it's back online, not even 5 minutes later, and here we are with the router online touting, can I draw? Yeah, all right, there we go. Touting a 110 priority. So I've got this 110 priority, and you've got a 90. What are we going to do with this situation? Well, by default in HSRP, nothing happens, okay? This is now the standby because the active is already in place. There's no election to be had because the router 2 over there on the right, it already won the election. It is the active router. And because it's the active router on the left, router 1 is on standby, and in theory, the life is good. We don't need to do anything. However, like I mentioned before, networks, we like it to be deterministic. We like to know where our traffic is going. And so what if I want, when that router comes back online, to take over for that, call it the standby router. It's now active. We want to take over router 2. Okay, there we go, router 2. So I want to take that back from router 2. Well, this is this concept called preemption. So let me clear that off, and we'll go back purple. So now, if I've got this preempt command configured, which again is not the default in HSRP, but we can configure it. With preemption enabled, what that means is now when I have the outage, so this goes down, we now have this router as the active, and then this router comes back online. Because I have a higher priority level, I'm able to take control back because I've configured preempt. I can preempt the existing active router. So effectively what that looks like is this active router now becomes the standby again, and this router's active state is restored. Now, why would I not want to do this? Well, what if this link right here is flapping? So it's flapping. It goes up, it goes down, it goes up, it goes down, it goes up, it goes down. So it goes down, maybe it's every 30 seconds or so it goes up or changes states. So after 30 seconds, it comes back online, it preempts, it grabs control back from the other router, but then it goes down again. Okay, that introduces network instability. When we don't like network instability, we want network stability. And so if we have a situation where we don't necessarily want to be able to preempt because this router might be going up and down. Again, we like deterministic networks, but I also like to be in control. And maybe I don't want it to come back up and immediately grab the active status again. So if I want to be in control, then what I can do is I can wait until after hours when nobody else is working or what have you, and I log in, I just do a shutdown on this interface. I just shut it down, let this one become the active, and then I do a no shut, and then it'll come up and it will put itself into a standby state. Okay, so I can manually do it. I can have it preempt. I tell you what, I see a lot of preempt. It's not a bad thing by any stretch. It's simply being aware of what's happening on the back end and the potential problems that it could cause. Okay, so yeah, we might not get to configuration tonight. It's 8:54. Holy smokes. All right, so that is HSRP. If you have any questions on HSRP, chime into the chat. I'll be sure to answer those to the best of my ability. Meanwhile, we're going to move on to VRRP. And this one, and this one. All right, here we go, VRRP. All right, so having understood, now that we understand HSRP, VRRP is largely just knowing the differences. So when I'm looking at VRRP, the first biggest thing I need to know, I've already mentioned it, it's an industry standard. This is not Cisco proprietary. Any router in the world could deploy VRRP. It's all good. If this shows up on a Cisco exam and it's asking you something about which protocol would you use, VRRP would be it if it's asking for an industry standard. Keeping in mind that HSRP version 1, HSRP version 2, and GLBP are all Cisco proprietary. You cannot run those unless you are a Cisco router. So if you don't have a Cisco network, you find yourself working on one, and you need a first hop redundancy protocol, guess what? VRRP is your only option, so you're going to roll with it. Now, we mentioned already this as well. We are not active standby, we are master backup. Okay, the words change. We need to be aware of that as much as anything because we might get asked it on a Cisco test, who knows. But at least, when you're looking at it on a network and you're doing a show VRRP command, you should expect to see master and backup instead of active and standby. Okay, interestingly, this is kind of an interesting one. Remember we talked about those priority values? So the same concept applies. It's the highest priority, highest IP address is the tiebreaker, but HSRP you can configure between 0 and 255. I don't know why this is, but VRRP has to be between 1 and 254. So we've lost 0, we've lost 255 as options. I suspect it's just Cisco was like, hey, we've got 256 numbers, use them all. And VRRP was probably like, you know what, let's reserve the first and the last because that's what we do in networking is we reserve the first number in a sequence, we reserve the last number in a sequence. So, yeah, that's what it did. All right. Here's the interesting, probably the most interesting component of VRRP and the most compelling reason. If you're going to sit back and say, okay, Jeff, if I have a Cisco network, what protocol should I use? And more often than not, if you're an all Cisco network, you're probably going to go with HSRP. But there is one compelling reason why you might want to go with VRRP over HSRP, and it is this. When we talk about virtual IP addresses, let's say we're .2 here on the master, .3 here on the backup. When we're talking about virtual IP addresses with Cisco, we have to have a third number, so .1. And indeed, with VRRP, we can also do .1 as the virtual IP address, right? Virtual IP address is .1. VRRP allows us to actually use the physical IP address of one of the routers. So VRRP IP, and then I can enter the .2 address. That would be the command. So if I'm making the router physical IP address be the virtual IP address, that has a pretty big implication. Two big implications, okay? The first one of which is we saved an IP address. Hooray, we saved an IP address. How much does that matter? Well, on a network like this that I've just drawn, it don't add up to a whole lot because this is probably a /24 network, 254 usable addresses, and now I went from, consuming 3 of those for my routers to consuming 2 of those for my routers. Okay, so I took my 251 back up to 252, big whoop-de-doo. Not usually very important. This can be really important when you have some situation like this, where I have 2 routers attached to a service provider router, maybe an internet router, and this is a /29. Well, if this is a /29 environment, a lot of times what that means is I'm consuming .1 here, .2 here, .3 here. /29 is 8 addresses, but only 6 usable. And so I'm already consuming 3 of them just with my routers. To use a 4th for HSRP, that's going to stink. Because I'm using 33% of my remaining addresses. I used 3 of my 6. I've only got 3 left. I'm going to use 1 of them for HSRP. So VRRP is a great solution for that scenario where you say, you know what? I need to reserve that address. I'm trying to do natting, or I'm trying to do, throw other devices on this DMZ network, or whatever the situation is. Be aware VRRP will save you an address. All right. So we do have applications with VRRP. Don't doubt that. That's the biggest one. So that's the, I called it an implication. It's not really an implication. It's more of like a benefit to VRRP. The implication is this: we can't have duplicate IP addresses on our network. So if .2 is my virtual IP address, and this router right here wins the election, so this router is managing .2. Well, what happens to this physical address over here? It's a duplicate IP address. I can't get rid of that .2. I can't shut it down. So, what's the solution to this? Well, the solution is don't let that other router win the election. All right? This might be why we can't use 255. I don't know why we can't use 0, but I think it's why we can't use 255. Now that I think about it. When we apply IP address .2 to the master in this case, or to when we apply the physical IP address as the virtual IP address, we're going to automatically configure a priority of 255. When I say automatically, I mean the router does it. Okay, Jeff doesn't have to do it. As soon as I configure that, it applies itself. It gives it the highest possible priority, so it cannot lose an election. And because it cannot lose an election, it's always going to be the master. And by the way, that means if it comes back on, like let's say it goes down and .2 is over here, and it comes back online, well, we're going to have preemption forcibly enabled as well. Because when it comes back online, it has to own .2. So again, the implication, it makes sense. The master's physical IP address, if it's also the virtual address, well, I shouldn't say it like that. If a router's physical address is the virtual address that's shared among many routers, the router that owns that physical address has to be the master when that router is online. I hope that makes sense. I hope that was clear. If not, chime into the chat and ask away. Okay. Interestingly, by the way, as we wrap up VRRP, because again, we don't have to spend as much time on VRRP because it's just HSRP with differences. VRRP does have preemption enabled by default. Okay. HSRP preemption is disabled by default. You have to explicitly enable it. With VRRP, if you don't want it to preempt, you got to say no preempt. Okay, so saying that it automatically enables it on master, technically it was already enabled unless you disabled it, at which point it will enable it because, again, that router, while it's online, must be the master. Okay. Whew. VRRP, everyone. On to GLBP. I tell you what, if you've been hanging out with us, and you're like, I already know HSRP or VRRP, but I'm going to hang out. This might be why you've been hanging out, because GLBP is just a protocol that we don't have a ton of experience with, because very few people use it, and so I get it that we just aren't as comfortable, generally speaking, with GLBP. All right, in order to discuss GLBP, we need a few more routers, so let's go ahead and get those colored in here. And there we go. So let's say we've got, that's getting sloppy. Come on, Jeff, make it look nice. I have no idea if that looks nicer, but in my mind it is. All right, so now we've got 4 routers on this network. And we've got some kind of common network uplink. I don't know. It doesn't really matter what's upstream, honestly. GLBP is called the Global Load Balancing Protocol. And it's interesting because with HSRP and VRRP, first of all, we only support 2 routers in the active and standby state. All right, just to kind of cover HSRP real quick. In this scenario, we'd have an active router, we'd have a standby router, and we'd have 2 listening routers. The listening routers, they just can't get into a standby state because there's no room. We have an active, we have a standby, and so I'm just left out in the dust and I don't do anything, okay? So active is, the only thing they can do is if the standby happens to go down, then one of these will become a standby router, right? I mean, that's why they're listening. You just never know what's going to happen. And if the active goes down, the standby will become the active, and one of the listeners will also become the standby. It makes sense. So all of my traffic with HSRP is going out the active router. So even if I only have 2, forget these 2 for a moment. Even if I only have 2 routers, I'm not taking advantage of both of them. I'm sending all of my traffic out one of those routers. Now, we can work around this. Here's a clever idea. What if these are layer 3 switches, or they could be routers with sub-interfaces, and this, I got rid of my green. Let me go back to my green. This, let's just call this, there we go, is VLAN 100. And then let's say I have VLAN 200. So these routers are on a separate network segment. I know it's a little confusing. I tried to draw it with different colors. And this is VLAN 200. I covered it up. VLAN 200. All right, there we go. Is there any reason not to use GLBP? That is the question of the hour, and I love that question. Any reason not to use GLBP? Mostly complexity and troubleshooting. People don't like it because they don't know it. And I will say this, there is zero reason to use GLBP if you only have, well, I gotta be careful with that. Let me finish this explanation. We'll come back to that. Okay, so we've got, where we're going with this. Oh, yeah. So this is HSRP. If I have HSRP and I am load balancing between VLANs 100 and 200, I might have the active and standby be what's in blue for VLAN 100. But for VLAN 200, I've got this router as the active and this router on the left is the standby. So I can load balance my traffic with HSRP. I just have to do it cleverly. I have to do it on a per network basis. And that works great as long as I've got multiple VLANs. So keep in mind some of the scenarios that we drew up here in the corner. Remember some of these internet edge scenarios? Whatever the situation is. Maybe with 4 routers, maybe we have 3 routers. In those situations, we only have 1 VLAN. And so GLBP might be a good fit for this if indeed I want to load balance between my routers. I don't want all of the traffic flowing through one router at a time. Now again, if everything is a gig link and my internet circuit through the whole thing is 100 meg or 250 meg or something like that, everything's a gig, sending it all through one router isn't the end of the world. It just feels wrong, I guess. So this is why GLBP is so seldom used, because I can load balance in many situations with HSRP. I just have to change the route, the active and standby configurations on a per VLAN basis. That's what I have to do in order to load balance. So I just have to get clever, like I mentioned. All right, so back to GLBP. What GLBP enables me to do is, if you can't tell, by the way, so far it seems like it's probably pretty clear at this point what we're about to say. GLBP allows me to load balance across all of these routers. Now, I drew it all with one PC there, but let's assume there's lots of PCs here. Okay, I can load balance my network, all of my devices, on a single VLAN across any of these routers. I can have up to 4 of them, which is why I drew 4, but you could do this with 2 or 3. You could even do it with 5, but the 5th isn't going to participate in the load balancing. It's going to sit there in the listen state. So, the way this works is we have 2 states we have to be concerned with. We have the active virtual gateway, AVG, and that equates to the active state in HSRP. It is the router that's in charge. And then we have active virtual forwarders. Active virtual forwarders, or AVFs, this is where we can have up to 4 of these. AVF, 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 AVF. So the active virtual forwarders are the ones that are capable of receiving traffic from the network and sending it upstream. These AVFs are running virtual MAC addresses. Each one has its own virtual MAC address, so that's important. Every AVF has its own virtual MAC address. And the AVG does all of the responsibilities that we've spoken about as far as the active is concerned. So the biggest thing it's responsible for is sending those ARP responses. By sending these ARP responses, the active virtual gateway, the AVG, is able to control on a per laptop basis, I don't know why I said laptop, a per host basis, right? Whatever device is attached to this network, the AVG is able to tell it which AVF to go out. It either sends it the first AVF's MAC address, or it sends it the second AVF's MAC address. We're talking about virtual MAC addresses here, so keep that in mind too. So we kind of have VMAC 1 here, we have VMAC 2, VMAC 3, VMAC 4. So if I want to load balance this round robin, which is the default setting, my AVG is going to it's going to alternate round robin with what my virtual MAC is that I'm responding with. So a host comes online, a host ARPs for the default gateway, the AVG is going to respond with, let's say, virtual MAC address 1. Then the next PC ARPs for it, and AVG responds to that with virtual MAC address 2. And then another PC, same thing, ARP request, ARP response comes back, virtual MAC address 3. Fourth machine fires up, does a ARP request, ARP response is virtual MAC address 4. What that results in is we have 4 different PCs or 4 different laptops, and they're using 4 different gateways. Okay, so imagine a network with 1,000 hosts. We could have 250 on every single active virtual forwarder. Now, there are different ways we can load balance. We can load balance round robin. Again, that's the default. We can round robin with this concept of wait. And if we do the weighted version, then it's kind of like round robin, except I can control the balance. So I could, for example, say that this host here on the right gets twice as much for whatever reason than the other routers. Maybe it's got a fatter upstream pipe. I mean, that's what it's designed for, right? Is, my internet service provider gave me a 100 meg circuit here, and they gave me several backup 10 meg circuits. Well, maybe I want 10 times the amount of traffic to go out that router. So I would configure the weighted version of load balancing, and the vast majority of my traffic is going out that one router, and the rest is getting load balanced with the other 3 routers. All right. And and so the third way, by the way, so we've got round robin, we've got weighted. These are the different types of load balancing. And we also have, what's it called? Host dependent, I think. I've got it in my notes. What's it called? Is it host? GLBP. Yes, it is host dependent. Never doubt. It's host dependent. Host dependent effectively says, I'm going to run a hash on your MAC address, Mr. Host. So you sent me an ARP request. I look at your MAC address. I run a hash. And based on that hash, I either get a 1, 2, 3, or 4, or something like that. And if I get a 1, I give you virtual MAC address 1. If I get a 2, I give you VMAC 2. And the reason why, so it's basically round robin in a way. It's not round robin in a way. The goal of host dependent is to make sure that you as a host always use the same gateway, no matter what. So if you log into the network and you're there for a little while, and then you log out of the network, and then later on you log back into the network and you do another ARP request, you're going to get the exact same gateway in that situation. And so, I don't have any specific applications to say why you'd use this, but like over round robin or weighted, but it's an option. Cisco gave it to us as an option. So one important note in all of this, by the way, is that if one of these active virtual forwarders goes down, we're going to, one of the other active virtual forwarders will pick that virtual MAC address up and run with it. So we do still have redundancy from that perspective. What if the AVG goes down? Well, the AVG uses these tried and true. We're familiar with this at this point. We've got priority. We've got preempt. Okay, the AVG truly equates to this active role in HSRP from that perspective. It's doing the ARP response, it's doing the ARP responses. It has the highest priority. It won the election. It has preempt configured. So that's that's the concept of active virtual gateway. Active virtual forwarders, I believe it's just the first 4 that show up. So it will assign itself as an active virtual forwarder, and then from there, the next 3 devices that show up will be active virtual forwarders as well. There is no election among the active virtual forwarders, to my understanding. Okay. So Papa, to your question, because it's a good question. Why not use GLBP always? Well, if you have 2 routers, I think the best way to explain it, I'm just going to stand by what I said before. It's fine. You could deploy it every time. You could 100% deploy it every time. The problem is only around complexity and familiarity. Most network techs are very comfortable with HSRP and VRRP. I should say HSRP or VRRP. And so they just wanted to play what's simple. I've only got 2 routers. I don't need GLBP to load balance. And I will say this, if you don't have a reason to need to load balance, there's not even really a strong reason to do it. Routers are pretty powerful these days. And like I said, we've got a lot of situations where we have a gig pipe, to the network, and then we've got like 10 meg upstream. And so like I've got plenty of bandwidth. I can handle this. I don't, the router's not going to get bogged down. GLBP was certainly invented in a time when routers could get easily bogged down. And so that's the primary reason it was built. I think that the primary application for your GLBP is going to be number one, sure, this rare situation where you have 4 routers or 3 routers. This doesn't happen very often. The only thing I can really, service providers, you could see this happen every now and again, but if service provider, not usually using first up redundancy protocols. But I've seen an internet edge where you've got like 3 routers going out to 3 different service providers. I have seen that. And the problem with GLBP, again, it's a good question because it's making me think too. The problem with GLBP in that scenario is you usually run BGP at the edge, and BGP gives you very intelligent, like, hey, that router is closer to Google than that router, according to BGP. So you want your edge routers to be able to decide to send to Google via the router that's closest to Google, and to Cisco.com, the router that's closest to Cisco.com. If you're using GLBP in that scenario, it'll work, and you'll load balance. You can even weight it according to the different internet bandwidths. But now you're load balancing by bandwidth, and you're not load balancing by internet, for lack of better words. You're not sending stuff to one website the closest way to that website. So even in those situations, you usually use BGP instead of GLBP. So I think it's like, I think in the end, I can't get away from the idea that it's just more complicated, and people don't like complexity, and understandably, it's harder to troubleshoot when a network is having problems. And so don't introduce the complexity unless you have an extremely compelling reason to do so. So if you have an extremely compelling reason to do so, then use GLBP. But if the question is, well, I've got HSRP running, could I use GLBP instead? The answer is, yeah, you absolutely could. One thing to be aware of, I didn't mention it, I should have. GLBP only has 1,024 groups, so be aware of that limitation. It's mostly because it's mostly that VLAN ID issue. So like you have VLAN 1500, you couldn't apply GLBP group 1500. That's more of a nuance. That's not really a reason not to use it, but it's something to be aware of. All right, but very good question. All right. Well, that was a lot in an hour and 20 minutes. We did not get to the lab, but that's okay. I think that this is a lot to digest, and will give you something to think about tonight. So I want to thank everybody for coming tonight. I guess call this news. I was supposed to be at Cisco DevNet Create next week, and I was really looking forward to that too, by the way. And Cisco made I think it's the right call. They decided to cancel the conference due to health concerns, everything that's going on out there today. In this moment, we've got some health concerns worldwide. And so they decided to cancel that conference. So I will not be here next week. I'm sorry. I will be back home. I will be home next week. But because the schedule, we've already scheduled out to say we're going to take a break next week. I'll have a free night, but I'm not sure what I'm going to do with it. So we'll figure that out. Just find something to do with the family. So everybody enjoy a study break next week. We're off next week. That would be March 10th. We will be back March 17th. I am excited to come back on March 17th because, again, we're delving a little bit more into the ENCOR content. And March 17th is going to be about network architecture. And so when you look at the ENCOR blueprint, section 1, you see network architecture. We're going to be talking a little bit about network architecture there. So be sure to come by in 2 weeks and talk network architecture if that is something that interests you. So again, thank you very much, everybody, for hanging out. Appreciate that. If you have any thoughts or questions, be sure to hit me up on Twitter at Kish Squared. For that matter, if you have any suggestions for like what you'd like to see covered, hit me up there. In the meantime, I'll see you next time. Have a good night, everybody.